Present myself. I'm Nisrine Laghmich, PhD student at the Faculty of Sciences and Techniques in Tangier, Morocco. What I'll be talking to you about is a numerical analysis to assess the indoor temperature distribution in large buildings by an integrated thermo-aeraulic zonal approach. So we are all aware that in the last decades, the population is becoming more and more demanding and aware of the need to ensure a comfortable living or working environment. In order to ensure this, the thermal study is no longer sufficient, either for engineering or for scientific research, which always aims to develop an explicit methodologies that can be used to approach the reality of the buildings without any experimentation. So the order of the presentation is as follows. First of all, I will be looking at the problematic and objectives. Then I will move on to methodology. Thirdly, I will discuss some of the obtained results. And finally, the conclusion. So the key issue of this study is the large buildings. According to Annex 26 of the International Energy Agency, it is considered large if one or more of the statements apply. For example, the occupied area should be small relative to the total value. In this kind of building, the notion of the indoor temperature variation within large buildings induces the notion of vertical stratification and/or horizontal temperature distribution. In order to accurately calculate stratified air conditioning load, it is particularly important to predict indoor thermal environments. This later can be predicted by two approaches, CFD, numerical approach, and zonal models. However, the application of CFD models remains limited in the engineering domain because of its computational time. However, the zonal model is considered as an intermediate approach between single zone and CFD models because the zonal method requires fewer zone division than CFD approach and provides sufficiently detailed results. This work, entitled Numerical Analysis to Assess the Indoor Temperature Distribution in Large Building by an Integrated Thermo-aeraulic Zonal Approach, is developed to respond to all of these types of constraints. In particular, for example, to reduce the computational time for modeling the temperature distribution by CFD approaches. Now we pass to methodology. This research consists in performing thermo-aeraulic zonal model using a coupling of TRNSYS and CONTAM. As shown in this figure, the indoor space is decomposed into subzones accordingly to horizontal and vertical directions. For the horizontal subdivision, three kinds of subzones are existed: corner, middle, and center subzones. This figure shows the example of the center subzone. To apply this methodology, we have chosen a building with these dimensions, and it is located in a city that is characterized by a hot Mediterranean climate. Now we pass to results and discussions. So now we will present one of the results obtained in the vertical stratification. A comparative study was conducted to evaluate the effects of occupancy and on the vertical gradient of temperature. As a result, we evaluate the impact of occupancy rate on the vertical thermal stratification. As we can see in right figure that the increase in indoor temperature caused by the number of occupants induces a variation in the transition zone. This phenomenon can be explained by the stack effect. Temperature distribution, a combination with natural light ventilation and international gains, has been evaluated. So a maximum difference temperature between the opposite subzones is about 3 degrees Celsius. It can be noted that the natural light ventilation is not sufficient to ensure acceptable indoor thermal conditions. To sum up what I've just said, that the advantages of the integrated thermo-aeraulic zonal model developed in this study are shown in this slide in 5 points.